we're in the midst of our discussion of magnetic fields, and as I mentioned, since we're meeting after a 1 week gap, I had highlighted 4 premises that we're going to touch, okay, in these couple of weeks. The first premise is, as we know, moving charges produce magnetic fields, B fields. The second premise is that a moving charge inside a B field experiences a force. The third premise we will deal with is the concept of magnetic materials. How do some materials become magnetic? What is meant by magnetism? Why are some materials non-magnetic? And the fourth thing that we will be dealing with is we would like to explain what is the role of this concept of moving charges and what really are magnetic fields. So we'll have to introduce some relativistic interpretation of fields. Okay? What are magnetic fields? Magnetic fields sometimes are just electric fields in disguise. One observer may feel a force and he may ascribe it to electric fields, and another observer in a different frame of reference can ascribe the same force to a magnetic field. So what is the origin of magnetic fields? What are magnetic fields really? And how do we use special relativity, which you studied in your mechanics course, to describe magnetic fields? So this will come right at the end because it's a very subtle concept. Okay? So these are all empirical observations that you've already seen, and we're developing them further. So we already started our discussion of moving charges producing magnetic fields, and we looked at the Biot-Savart law, another empirical relationship which tells us that the magnetic field is simply given by mu naught over 4 pi due to a charge QV crossed with the position vector at where you want to find out the field from the moving charge divided by the distance squared. And another form of this relationship is that if you have an ensemble of charges, a large number of charges, these moving charges constitute a current. Okay? So another form of the Biot-Savart law is mu naught over 4 pi. This QV is replaced by IDL. Okay? Crossed with R over R squared. I hope you've seen the question in the tutorial as well. So we'll be looking at more examples of this. So this is where we finished off our discussion in the previous lecture, and we found out the magnetic field due to a straight wire of finite length. Suppose we would like to find out the magnetic field at a distance r from this current carrying conductor. It turned out that the magnetic field B, its magnitude is simply given by mu naught times I, the current that flows through this system, through this wire, divided by 2 pi r. And no matter where you go around this wire, this magnitude of the magnetic field remains the same. And if you look at this magnetic field from the top, if I view the magnetic field from the top, this is the point where the conductor is intersecting the plane. The field simply goes around in a circle. I can use the right hand rule, I can find out the direction of the field. Okay? So the field is circular. So a moving charge can give you a circular field, even though we cannot have an electric field of this kind due to static charges. Okay? Because of conservation of energy. So this is where we finish our discussion. And then I asked you to find out or derive the magnetic field due to a loop that is carrying some current density being J or some current I, and you have the axis of the loop, and you had a point P at a distance z0 above the loop. So was anyone able to find out the magnetic field? Anyone who's done this, I'll give 5 extra marks for the midterm. Has anyone been able to do this? This was the homework. Anyone in a class of 140 students? 5 extra marks behind. Excellent. This one son. Anyone else? Well, please note down Rizwan's name. Has anyone been able to find out the magnetic field at point P? This I gave as a homework. It was 5 marks in the midterm. किसी ने किया? Behind.
Not exactly what I tried. I don't even know I did it. It would be something of this sort. Something of this sort. And I just, it's just this. The calculation is in them somewhere else.
Alright. So what's your name?
Furkan.
Furkan gets extra 3 marks. Okay. Now I would like to find out the magnetic field. I thought you would have done this. Have you done it right now? Abhi kiya? तो बाद में देखेंगे. ठीक है, I thought you would have done this because that would have eased my task a little bit, but I can't proceed without calculating this magnetic field. Okay? So please, if I give a homework, it's worth something, even in material terms. Because we always think about material terms, right? Grade, GPAs, what grade am I giving on the mean, etc., etc. Okay? So, this is the least incentive that I can give you. Okay, so it's worth something. Alright, so I'm interested in finding out the magnetic field due to this loop of current. Okay, it's a moving charge and the charge moves in a loop. So I have to set up my geometry. I'm at this point P, it's at a height Z0. Okay, from the center of the loop, and this point is on the axis of the loop. Okay, and the current flows through this loop. The current is I. The current, of course, is a scalar. So sometimes if I write down the symbol J, it's with the vector sign. Now what I would like to find out, since there is cylindrical symmetry here, okay, I can look at this loop from the front. I can define my axis. This is my x-axis, this is my y-axis, and this is my z-axis. Let's look at this section of the wire. Okay. Now if I look at this section of the wire, what direction is the current pointing in? If I'm looking at the loop from the top, right? What direction is the current pointing in? It's out of the plane of the paper, so it's out of the plane of the paper here. Okay? And here, it's into the plane of the paper. Okay? So I have to note down the direction of the current because the direction comes in here. I have to set up this vector. Okay, this vector and this vector, and then take the cross product. So if I look at this small section of wire of length dl, okay, I break up this ring into small sections. dl is now a vector that is pointing out here, and it's pointing in here, and it's pointing in different directions all along the loop, but I just choose 2 points. Okay, I can choose as many points as I like, but for setting up the problem I choose 2 points. Now I would like to find the position vector of this point with respect to the element. So this is my the position vector is pointed like this, and it's a unit vector. So the position vector points like this, R. Okay, And if I look at the current carrying element, the small element dl, what direction is it pointing in? It's out of the plane of the paper. So here, I can draw a vector that's pointing out of the plane of the paper. I can take this vector and place it anywhere on the blackboard, okay? The vectors can be displaced. So I can join the tail of this vector with this vector. So now what's the angle between the element and r? It's 90 degrees. So the position vector is pointing outward, and the current carrying element, its length or the current is pointing outwards. So the angle is 90 degrees. Okay. Now if I look at this point from this vantage point, okay, I'm looking at this point from here. What do I see? I can draw a plane, okay, that is inclined. And if I look on this plane from the top, r is pointing like this, and dl is pointing like this, right? Which means dl is actually pointing along the x-axis, it's pointing outwards, and r is pointing in this direction. Okay, is this clear? So dl is, I'm looking at this plane from the side. Okay, I see the front of the plane is like this. Okay, this is the plane that I've drawn here. And when I view the plane from here, r is pointing upwards and dl is pointing laterally like this. Okay. So dl cross dr, I have to find the vector product. Now there are two possible directions of the magnetic field due to this current carrying element. It has to be normal to this plane. So the magnetic field can either point like this or it can point like this. Okay, it has to point perpendicular to the plane that contains dl and r. That's the property of the vector product. Correct? It's normal to both the vectors, dl as well as r. So it has to point normal to this plane. Now this plane has two faces, the top face and the bottom face. I have to choose which face. I have to choose one face. So I just use the right hand rule, take my first vector dl, curl my right hand fingers into the direction of r, my thumb is pointing upwards. Okay, so the magnetic field due to this small element which carries current is pointing in this direction. This is my small dB. Okay, this direction is eliminated. So I make a plane that contains my position vector and the dl vector, and I choose which face. I choose one face. Okay, for that I use the right hand rule. So dl cross with dr, I curl my fingers, my thumb points upward, so the magnetic field is pointing upwards in this direction. It's pointing in the YZ plane. Okay, so it's pointing in the YZ plane but upwards, not downwards. Alright. Likewise, if I take this current carrying element, okay, I can draw a new figure. Let's draw a new figure so that this figure is not cluttered up. Okay. Now here is my current carrying element into the plane of the paper, and my position vector r is now pointing in this direction. This is my r. Okay. Now my dl is pointing into the plane of the paper. Okay. So the angle between dl and r is still 90 degrees. But I have to choose the direction of the magnetic field that comes out as a result. Now if I draw a plane, I can draw a plane which contains this vector, okay, that's now inclined like this into the plane of the blackboard. Okay, and I view this plane from the top, from here. This is what I see. R is pointing upwards and my dl is into the plane of the blackboard. This is my dl, this is my r. So dl is into the plane of the blackboard, dl is into the plane, r is like this, and I form the cross product, dl cross r. I get my magnetic field that's pointing upwards again. It's not pointing downwards. So I have my right hand finger into the direction of dl, which is into the plane of the blackboard. I curl my fingers into the direction of r, which is upward. My magnetic field is pointing up. Okay, so due to this current carrying element, the magnetic field is again pointing in the upward direction, dB. Okay, so I have a magnetic field due to this element, I have a magnetic field due to this element, it's again pointing in the upward direction. So I choose any point on this path, all points are equivalent. Okay, all points are equivalent. Correct? There is no difference between this point and this point and this point. All of these points will produce a tiny magnetic field that is all pointing in the upward direction. So if I close up on this point P, my magnetic field due to the tiny elements inside the current carrying loop, they are all arranged in the form of a cone. Correct? This is my point P, and all the tiny magnetic vectors due to these tiny current carrying elements all along the wire, they form a cone. Okay, and this angle of the cone, this angle is, let's call it theta. Now if you observe, the magnetic field of course is the vector sum of all of these vectors. Okay, what direction is the net magnetic field going to point in? Upwards. Because all the horizontal components will cancel out. Okay, so if I look at this this arrangement from the top, I draw a plane. The horizontal components are all pointing out in all possible directions. These are just the horizontal components. The components of B that are in the XY plane. Okay, in this plane, XY plane, in the horizontal plane, and the vector sum of all of these horizontal, the sum of all of these horizontal components is 0. So I'm only left with the vertical component of the magnetic field. So the magnetic field at this point is just pointing upwards. Okay, this is B, and it's the sum of dB Z, right? All the Z components of the magnetic field. So this magnetic field will have a component along the Z axis. All of these magnetic fields will have a component along the Z axis. And you have to add them up. Will the components along the Z axis of the tiny fields be equal? The magnitudes will all be equal because all of these points are equivalent. So I have to take the sum of all the Z components of the individual fields. Since this is a vector, I would like to put a unit vector here to make this equation vectorially consistent. Okay, so this is the net field that I would like to calculate. Okay, so if I perform my calculation, my dB due to a small current carrying element, okay, now I'm only talking about the magnitude so far, is mu naught over 4 pi, the current through this element I, dl crossed with r. Okay, the r, what's the magnitude of r? 1. Sine of the angle between dl and r, what's the angle? 90 degrees. So sine of 90 is 1 divided by this distance squared. Now what is this distance squared? If this has radius capital R, so this distance squared is simply r squared plus z naught squared. So this is the magnitude of this blue vector, of each blue vector. Okay? And this magnitude is the same. And the z component of this magnitude, dBz, if I define the angles such that this angle is, I call this angle theta, okay, if this angle is theta, what is this angle? It's 90 minus theta. Okay. Okay, I have to find out this angle. I've called this angle theta already. So this angle is theta. Okay. So dBz is dB cosine of theta. Okay, and dB is mu naught I dl 4 pi r square plus z naught square. And what is cosine theta? Cosine theta is simply z naught divided by this side, by the hypotenuse. Z naught divided by the hypotenuse, I get 3 by 2 here. Okay. I give you half a minute to just think about this. Right, this angle is not theta, this angle is theta, which makes this angle equal to theta. Okay, let me draw this figure again. Okay, if I define this angle to be theta, this is r, this is z naught, right? एक मिनट है. This is R, okay? Okay. Now, if I look at the magnetic field is pointing in a certain direction. Okay. Due to this, it's pointing like this. It's normal to the position vector, right? Now this is the position vector, okay, due to this point. Due to this point, the position vector is like this. So this is the position vector, R. The magnetic field B, due to this element, which is dB, is pointing like this. It's normal to the position vector, right? I have called this angle theta, okay? Now if this angle is theta, what is this angle? 90 minus theta. So what is this angle? 90 minus theta. So what is this angle? Theta. So if I would like to take cosine of theta, it's R. There's an R here. Okay? Correct? Are you with me on this? Alright. Now I would like to integrate this. Now how do I integrate this? What is my variable? My variable here is dl. Can I set this dl in some other variable so that I can integrate easily? आप बताएं dl को किस तरह एक्सप्रेस करेंगे किसी और वेरिएबल की टर्म्स में? यहाँ तक समझ आ गया? सही बताओ. क्लियर है ना? ये एंगल्स का क्लियर हुआ ना? इज दिस I've defined this to be theta, this is 90 minus theta, this is 90 minus theta, and this is theta. Okay? So this is my magnetic field Z component due to a small current carrying element that's placed here of length dl. Now I have to go over the entire ring. Okay. So how do I integrate? What are my variables of integration?
Because I have actual for
Z axis के दरमियान है. बताओ. Why 2RD5? Why is the factor of 2? No. The circumference of course is 2 pi r, but if I would like to draw a circle, if I look at this circle from the top, I take a small arc length dl. If the radius is r, then the angle that this small element which makes at the center, suppose it's d phi, then this arc length dl is r times d phi. Okay, so I just replace dl by r times d phi. So this equals mu naught I r square d phi divided by 4 pi r square plus z naught squared 3 by 2. Correct? Now I have to find the total magnetic field. The total magnetic field B, which is all in the z direction, Bz, its magnitude is just the integral of the small dv's. Okay? Now this is mu naught I r squared, everything is a constant, 4 pi. Is this a constant? Yes, it's a constant, r squared plus z naught squared 3 by 2, and here I have d phi, where phi goes from 0 to 2 pi. Okay, because I have to go in the complete circle. So this magnetic field B turns out as mu naught I pi r squared. Putting this in parentheses for a reason. 4 pi r squared plus z naught squared 3 by 2. Okay? And there's a 2 here. Okay? So this is my magnetic field. Due to this current carrying loop on the axis only, I'm talking about the axis only, I'm not off the axis. Okay? If I'm off the axis, I can still do the calculation, but the integrals turn out to be more complicated. They're called elliptic integrals. Okay, so this is the magnetic field, the magnitude. Now, if I'm very far off from this loop, which means that this point is really far away from the loop, or in other words, this loop is really small. It can be either way. I can be far off from the loop, or this loop can be really small. It's one of the same things. Which means that my Z naught is much larger than R. Okay, let's see what happens to this expression. B equals 2 mu naught I pi r squared 4 pi. Now my Z naught is much larger, so I put a Z naught square 3 by 2 1 plus r squared over z naught squared 3 by 2. Correct? Now this quantity is much smaller than 1. It's a very small number. So I can use the binomial expansion 2 mu naught I pi r squared over 4 pi z naught cube 1 plus r squared over z naught squared raised to power minus 3 by 2. Okay, now from this expression I can move on here. I get a really nice result, 2 mu naught I pi r squared 4 pi z naught cube 1 minus 3 r squared over 2 z naught squared This is approximate because I've neglected higher order terms. Now if this is much smaller than 1, I can neglect even this term. Okay? So I'm left off with 2 mu naught I pi r squared 4 pi z naught cube. Now this is an extremely important result. That's why I've gone to the labor of doing all the calculations for you. Okay, otherwise this is stuff for the tutorial and recitation. Okay? Now why is this result significant? If I have an electric dipole, okay, positive charge plus q minus charge minus q separated by some distance, say s. Okay, what's the electric dipole moment for this dipole, right? What's the dipole moment? Its magnitude is qs, okay? And it's a vector that points from the negative charge to the positive charge. This is the convention of defining the electric dipole moment. This is electric dipole. Now if I am on the axis of this electric dipole, okay, and I'm really far off, really far away, at some point P, which is at a distance z0 away from the center of the dipole, if I'm this far off and this z0 is really much larger as compared to this s, then the expression for the electric field at point P that I obtain, which you can do on your own and which you've already done in class, is 2 times the magnitude of the electric dipole moment P, which is simply q times s, divided by 4 pi epsilon naught z naught cube. The electric field, as you all know, has a 1 over distance cube dependence. Now for this current carrying loop, the magnetic field at a distance that's far away from the dimensions as compared to the dimensions of the loop has exactly the same form, provided we make some adjustments. This 4 pi is of course common. The z0 cube dependence is common. Instead of epsilon naught, here we have mu naught, but on the other way around, because the speed of light squared is 1 over epsilon naught mu naught. Mu naught and epsilon naught have an inverse relationship, which means epsilon naught is 1 over c squared mu naught. Likewise, mu naught is 1 over c squared epsilon naught. So they have a reciprocal relationship. Okay? The value of mu naught is defined. This gives us a concise value, an absolute value of the speed of light. The 2 is common, and what remains is that this P, which is the electric dipole moment, is now replaced by this quantity, I pi r square. Now what is I? It's just the current through the loop, and what is pi r square? Is the area of the loop. So we can define a magnetic dipole moment in complete analysis with the electric dipole moment, mu. Okay, so this mu is the magnetic dipole moment. Sometimes you put a small m with it as well, or you can leave out the mu m. It's I times the area of the loop. Since the electric dipole moment is a vector, this must also be a vector. So I can put an area vector on top of the area, and this becomes the vector. So what's the direction of this area loop? You have to curl your fingers in the direction of the current, because the loop has 2 normals, up and down. So you have to make a non-unique choice. So you curl your fingers in the direction of the current, your right hand thumb will point in the direction of the area vector. Okay, so this is the definition for the magnetic dipole moment. Okay, and if you're far away from the magnetic dipole moment, the field will fall off as 1 over cube of the distance. Now this dipole moment can point in any direction, which means that if we have a loop that is carrying a current, okay, and they are pointing in all possible directions, then this loop will produce a current, this loop has a current, it will produce a magnetic moment pointing in this direction, this will produce a magnetic moment pointing in this direction, this will produce a magnetic moment pointing in this direction. So you can have these current carrying loops, small loops of current. Okay, and each time you curl your fingers in the direction of the current, your thumb will point in the direction of the magnetic moment. And if I just consider this loop and I'm at a point far away, then the magnetic field due to this loop is just going to point along the direction of the magnetic moment. Okay? So I can put a vector sign here, I can put a vector sign here. Likewise, I can put B equals 2 times mu, the magnetic moment, divided by 4 pi epsilon, 4 pi, there is a mu naught as well, 4 pi d naught cube. So the direction of the magnetic field is the same as the direction of the magnetic dipole moment. Okay, so here the magnetic field B is going to point parallel to the magnetic moment. But if you go really far off away from the magnetic dipole moment, the field is going to diminish as 1 over r cube. Okay, that is something important to recognize. Any questions up to this point? Because it's a central concept. So even though a static charge produces an electric field, in the realm of magnetism, a moving charge, which is called a current, produces a magnetic field. So the correspondence between a static charge is what static charge is to electricity is what a moving charge is to magnetism. That's the analogy. Okay, there are electric dipole moments in electricity, magnetic dipole moments in magnetism. Both of them act as dipoles. So a coil, such as this coil, can have a magnetic moment. Okay. Now if I look at an electron inside an atom, we've already studied these objects in modern physics. If you look at the electron, it has some orbital angular momentum. Suppose I just take the simple Bohr model of an electron. An electron is going around the nucleus, simplistic model, okay. The radius is, suppose, A naught, the Bohr radius. Now what's the current due to this moving electron? How do I calculate the current? What is the current due to this electron? Of course it's a circulating charge, it carries some charge. The charge is minus E. So what's the current due to this circulating charge? Please calculate the current, I would like to see. A circulating charge must have a current. I want to find the magnetic moment of this circulating electron, so I need to find the current. Current is charge per unit time. How much charge flows through a certain plane normal to the motion of the electron per unit time. Yes, charge divided by some time. Okay, time period is going on. Velocity के अलावा भी फैक्टर होगा. Good. V लिख लो, V. ठीक, आगे चलो थोड़ा सा, ठीक. All right. So the current is how much charge flows per unit time. Minus E. Suppose I want to find this electron is circulating around the nucleus in the simplistic Bohr model, right? And its time period is T, suppose capital T, okay? So it makes one revolution in T, time T. So how much distance does it cover in time T? It's 2 pi a naught. 2 pi a naught. Suppose its velocity is v. Okay, so this is the current. The magnetic moment of this electron, I'm putting an m so that we not confuse with permeability. Mu m is I times pi a square minus a over 2 pi a naught pi a naught squared v. Okay, so this pi goes away. And I'm left with mu m equals minus e over 2 a naught v. Okay, now I multiply this by m and I divide by m, the mass of the electron. Now what is this quantity equal to in mechanics? A naught v into m. What is this quantity? This is given a special name in mechanics. It's the angular momentum of the electron. Okay, orbital angular momentum. पढ़ा है ना orbital angular momentum? पढ़ा हुआ है ना? Minus e over 2m l. So if this is a vector, mu n is also a vector. Indeed it is. So the magnetic movement of an electron inside an atom given by minus e 2 over m into the orbital angular momentum. Okay? It's a very important relationship. Now what this relationship tells us is that if you have an electron in the s orbital of a hydrogen atom, what is its angular momentum there? What is L, small l or capital L in the s orbital? Small l क्या value होती है s orbital में? ये small quantum number में L is 0. The magnitude of this angular momentum operator in quantum mechanics is given by L into L plus 1 under root h bar. Have you studied this? So if this angular momentum is quantized, then the magnetic moment is also quantized. Okay? So whenever you have orbital angular momentum or angular momentum of any kind, the magnetic moment exists. Right? The strange thing is that it also exists for uncharged objects. But that's beyond the realm of this course, that's because of quantum mechanics. If your angular momentum is 0, the magnetic moment associated with the angular momentum is also 0. Okay? If small l equals 1, for example, in the p orbital of the hydrogen atom, you know that in the p orbital l equals 1. Okay? So your magnitude of the orbital angular momentum equals under root 2 h bar. So your magnitude equals minus e over 2m into under 2 h bar. Now this is the vector equation. I can take components of these vectors. So if I take the component along the z-axis, minus e over 2m, the component of this vector on the z-axis, suppose I call it Lz. This will give me the z component of the magnetic moment of the electron. Okay? So whenever there is angular momentum of a charged particle, even if it's inside an atom, that electron will act like a magnetic moment. A magnet, if you look at a magnet, a permanent magnet, and you know that I don't like to draw lines that intersect this body. So I will draw a magnetic moment that's pointing in this direction, mu m, that represents the magnet. So if I look at this object, its magnetic field is going to have a pattern like this in space. Okay? Inside, the field goes like this. So this is the pattern of magnetic field into a bar magnet or cylindrical magnets. Magnets of this kind. Okay? It has a magnetic field that resembles this. Now, what we've learned is that this bar magnet can be replaced by a magnetic dipole. This bar magnet is indeed a dipole. So it's totally equivalent to a current carrying loop which has current flowing in this direction. So this magnetic dipole, which is a current carrying loop, will produce a magnetic field that is identical to the bar magnet, like this. Okay, so this magnetic dipole, which is just a current carrying loop, will produce a field that's identical to a bar magnet. Or in other words, the bar magnet acts like a dipole. The Earth acts like a big dipole. And you can always model the magnetism of Earth by a current. Okay, so this is a homework problem. If you have a current, if you have a coil that is wrapped around the equator, and you have a magnetic field of the Earth, say 1 gauss, at a distance at some 100 kilometers away from the Earth, how much current would you need to go around the equator to produce such a field? Okay, so the magnetism of Earth can also be modeled by a current carrying loop, a loop that is wrapped around the entire equatorial belt. Okay? So whenever you have a physical current carrying loop, it acts like a magnetic dipole, just like a bar magnet. Okay, and the strange thing about this relationship is that whenever we have angular momentum, we have associated with it a magnetic moment. And in the 1930s, a strange experiment was performed by Stern and Gerlach, and it was an accidental discovery. And I'll share you an article that shows how cigar smoke changed the fate of physics for all time to come. So what they did is they took silver atoms inside an oven. The oven had a tiny opening. There were lots of silver atoms. Okay, and in silver atoms, the valence electron is in the x orbital, so its orbital angular momentum is 0. So this was at high temperature, it's an oven, it's being heated. Silver atoms came out of this tiny slit, okay, and they were passed through a magnetic field. So a north pole and a south pole with a taper to produce a non-uniform field. Okay, so a non-uniform field was produced. Okay, if you do the Hall effect experiment, it has two magnet pole pieces produce a uniform field. If you make one pole piece flat and the other conical, it will produce a non-uniform field. Here they place the screen. Now, according to what we've observed here, if the valence electrons of silver atom are in the s orbital, they should not have any orbital angular momentum, and they should not behave like dipoles. They should not behave like magnetic moments because their magnetism is 0. However, when they pass these silver atoms through this non-uniform field, they observed two spots. Okay, which means that the beam of silver atoms was split into two. They show that even in the absence of orbital angular momentum, there is some other kind of angular momentum that is called the spin. So this is how spin was discovered. The spin has nothing to do with orbital motion. So in addition to the orbital angular momentum, there could be another property called the spin, S. This S also produces a magnetic moment. So if I have something that has orbital angular momentum, an electron that has an orbital angular momentum, like an electron in the p orbital, and it always possesses spin. Spin is always there. Just like an electron has a charge, it has a mass, it can also have a spin. So there is minus d over 2m, there is a magnetic moment due to the orbital motion, and there is a magnetic moment due to the spin motion. The only difference is that there is another factor here of 2, which comes out because of relativistic quantum mechanics. Okay? And this gives us the total magnetic moment of an electron. It is contributed both by the orbital motion and the spin motion. And the spin is not motion. So if we have silver atoms, if this is 0, still there will be some angular momentum and it will cause the magnetic moment to be non-zero. And the point is that the beam is only deflected into 2 parts. So if this is the z-axis, the z component of the spin only has 2 possibilities, plus h bar and minus, plus half h bar and minus half h bar. This is how the spin quantum numbers were discovered. So magnetism is a profound property of subatomic particles in all matter. Okay? And with this concept of the magnetic moment, you can actually do wonders. Okay? Now this is what I wanted to say about the first premise. The moving charges produce magnetic fields. Now I would like to move on to the second premise. I give you half a minute just to think upon all of this and then we'll continue. Alright, now I would like to show a demonstration with which to start off the second premise. Moving charges are affected by magnetic fields. Okay, the first premise was moving charges produce magnetic fields. Now if there is a magnetic field and charges move through the magnetic field, a force acts on them. Now the simplest way I can demonstrate this is using this oscilloscope. Now if you look at this oscilloscope screen here, so what I have here in front of you is an oscilloscope. I've taken out the cathode ray tube outside the oscilloscope, and what is in front of you is the screen. On the screen you can see a tiny spot. So there's a beam of electrons that is coming in your direction, into your faces, and it's hitting on this phosphor screen and giving you this glow. So this is just the image of electrons, the glob that electrons produce on the screen. So really we have a stream of electrons flowing through this tube. Okay, and these electrons are moving at really high speeds, say 20 to 30% of the speed of light. So relativistic speeds are not difficult to obtain. You can obtain them on a desktop. Of course, can you zoom in a little bit? Can you turn off the lights a little bit? So I can of course produce an electric field and deflect these electrons because these electrons are charged particles. Now how can I produce electric field inside the oscilloscope? Of course I can just change. Okay. Okay, I'm applying an electric field on the vertical plate inside the oscilloscope, and I can move this beam up and down. I can move the beam of electrons up and down. So there is a force acting on the electrons, and this force is actually deflecting the electrons up or down. But this is an electric field. Agreed? It's an electric field because inside the does anyone know how an oscilloscope works? Let me draw a diagram for this in okay? Basically, I have a filament that is producing electrons. There's a high voltage. This screen is positively charged. This is negatively charged. Electrons issuing from this filament due to thermodynamic emission are accelerated towards the screen. That's why they move. I have vertical deflection plates, and this can be made positive, this can be made negative, and if I have a plate of this kind, the electron will be attracted towards the positive plate and they will deflect. If the potential is smaller, they will deflect less. If the potential between these plates is zero, they will not deflect at all. So what's happening here, if you look at the electron, an electric force is acting on the electron. Fe. This electric force of pure electrical reason is deflecting the electrons up and down. In the potential direction reverse, the electrons will deflect downwards. So that's what I'm doing here. I am changing the electric field on the plate so that this spot is moving up and down. I can also apply a voltage on plates that are vertical, but the electric field will be horizontal. So I can I have plates inside the oscilloscope in this direction, and the electric field can now be applied in the horizontal direction. And the force can be applied in the horizontal direction so that this beam can move in the horizontal plane as well. So I can make these electrons move in any direction I like by the application of electric fields. Now if I have a magnet, it's a permanent magnet, I can produce the same effect of motion, of force acting on these electrons with this magnet. Okay? Just want to wear my gloves because it's a higher voltage, several thousand volts. So don't try this on your own. You have to be careful when you do experiments. So I can just deflect this beam using a permanent magnet. Which is another argument. Okay, so this is a permanent magnet. Now the question is, if this has a magnetic field, what is the current that is flowing in this magnet that is producing the magnetic field? Because moving charge is producing magnetic field. So what's moving in here? There's no current in here, no conventional current. This is the topic of the third premise. How are materials magnetic? Okay? मैं पूरी एक स्टोरी बनाना चाहता हूँ आपके सामने. आप पढ़ लेंगे, इंजीनियर्स बन लेंगे, सब कुछ हो जाएगा, बहुत अच्छा हो जाएगा. लेकिन विजडम के अंडरलाइन थ्योरी क्या है? Okay, now I have this permanent magnet, no current flowing through. Of course, it deflects a compass needle, but let me show that afterwards. If I move this magnet close, you see, to the electrons, the beam of electrons is deflected. Okay, so I can just have this permanent magnet. I can move it close. You can see the magnet at the top left. Okay, and I can change the position of this electron. Now if you observe, the velocity of electrons is straight into your face, the magnetic field due to this magnet is horizontal and the force is vertical on the electron. So all three vectors, force is a vector, the velocity of electrons is a vector, the magnetic field is a vector, all three are vectors and all three are perpendicular to one another. All three are normal to one another.
The downward direction
अब आपको क्या पता है इसका डायपोल इस तरह मैं तो आई जस्ट रोटेट इट. ओके, नाउ लेट्स सी व्हाट हैपेंस. जो भी है नोट और सब जो भी ठीक है, so use the right hand move to find itself. Okay, I move it closer. This is like a dipole. The magnetic field changes as 1 over q of the distance. I move it closer, the field goes up, the force goes up. Okay, if I have the, I can move it in the other direction. You see, now I'm at the top. I'm at the top. Now the electrons move horizontally. Again, all three vectors are normal to one another. Okay. If I make this line really parallel to the electrons, it shouldn't move, but it's difficult to make it really parallel. Okay? So this is how a permanent magnet that has some remnant magnetism can affect moving electrons by producing a magnetic field. Okay? The same effect, however, can also be observed if I don't have a permanent magnet, rather I have a coil. Now the coil from a single loop, single turn, the magnetic field is really small, so we have many turns here. Is this not focus turn? So now what we have here is basically a solenoid. Okay? Many turns in many layers. It's a big solenoid. Okay? And it produces a magnetic field. Now, what direction is this magnetic field going to be? Horizontal, vertical, what direction? It's going to be horizontal, along the axis. But then it will have a pattern like this. Okay? Along the axis, right in the middle, it's going to be parallel to the axis, and then it's going to diverge out, diverge or converge, depending upon the winding and the direction in the current flows. Okay? The same effect of applying a force on the moving electron can be seen if we don't have the permanent magnet, which can move far, far away. Okay? I don't want this to interfere with anything else. This is a compass, I'm moving away, okay? And I can just produce now, I can make this become a dipole by the passage of current through it. Okay, let me do that for you. So my purpose is to show that current carrying loops produce magnetic fields and they can exert forces on moving charges. And then here we've seen exerting forces on electrons. There's an experiment in the lab that actually demonstrates this as well, to find the charge to mass ratio of electrons. Okay, so I turn on the output. Nothing happens because the current is still zero. Simply that is forward moving. The current here is 0.2 amperes. Okay, the current is seen to increase, and as the current increases, the magnetic movement of this solenoid, of this current carrying loop goes up, and the force that it exerts must be going up. We haven't yet looked at the formula of the force, but it seems that the force depends on the current, which depends on the magnetic movement. Okay? The current is now at 0.5 ampere. I would like to make it go down because I don't want the coil to overheat. Okay. If I have a Gauss meter which measures the magnetic field, I can use this Gauss meter to detect what magnetic field is being produced here. So, can you come here please? Can you just tell me what the magnetic field is? आपने ये रीडिंग पढ़नी है, ठीक है? इसको ऑन करता हूँ. Can you see the field going up?
Yes, sir.
What's the value of the field?
7.4, 9, 10.
Units?
10.4 G.
G क्या है?
0.1.
ये G क्या है? किस चीज का यूनिट है? गॉज। एक टेस्ला में 10,000 गॉज होते हैं, ठीक है? इट्स नाउ 42 गॉज, 45 गॉज, ओके? तो एक टेस्ला में 10,000 गॉज होते हैं। अब ये पकड़ो और मैग्नेटिक फील्ड इन दिस मैग्नेट फाइंड करो। दिस मैग्नेट विल हैव अ मैग्नेटिक फील्ड ऑन इट्स ओन, okay? If I move the magnet close, the field goes up 50 gauge, 80 gauge, 90 gauge, 130, 200 gauge, okay? If I move this field really close to this Hall center, the field can go up. Now if you, okay. Now if I turn on the current, turn on the supply again, you can see that, is the focus for this? Electron will get it downwards. Okay? I increase the current a little bit more, the deflection goes higher. Okay? Now what I would like to do, I would like to turn off the voltage, the current, turn off the power supply, and I would like to change the direction of the solar lamp. I've just changed the direction of the solar lamp. Now what do you expect? The electron will go around in the opposite direction. Okay? I have to be very careful with this direction of this time, okay? So I turn on the supply, turn on the voltage, the electron will now be deflected in the opposite, and they're not going vertically upward, they're going in a diagonal, along the slanting direction. Why is that? Right, because the height of the electron beam and the axis of the solenoid is not the same. Okay? The magnetic field is pointing in some slanting direction. You can find out what direction the magnetic field is pointing by looking at the deflection. You look at the angle of the deflection. You can actually find out the direction of the force. So what we've seen here is that not only can current carry loops, they can produce magnetic fields. Those magnetic fields can affect moving electrons, moving charges, moving particles of any kind. Okay? And there is a simple way to calculate the forces. So in the last 10 minutes I would like to... Ji? Kya hua? Force on moving charges. So if I have a charge Q, okay, it's moving with a velocity v, which of course is a vector, then there is another empirical relationship. It's not a law, but these empirical relationships are also a law, for example, Coulomb's law. Okay? There is an empirical relationship that helps us calculate the force on this moving particle, and that relationship is that QV crossed with the magnetic field V. This is the force. It's also called the Lorentz force. And if there is an electric field at the same time superimposed on the particle, you can add a Q times E to it. Okay? Now, this is something you need to remember. Of course, you've seen this in your A levels and FSC. So this is the Lorentz force. If I have a particle moving with a velocity v, that is at a certain angle to a magnetic field at this point v, then the force will always be, number one, no. There is no electric field by the way. The force is always going to be normal to both these vectors. So I draw a plane in which this velocity vector and the magnetic field is, and I draw a plane This plane is just a plane of the blackboard. So the force can either come out of the blackboard or into the blackboard. It has to be normal to this plane. So I just use the right hand rule, point my fingers into the direction of velocity, the first vector, curl in the direction of the field. The force is now going to point outwards. Okay? So the force is outwards. Okay. Now if I, instead of a single electron or a single charged particle, so by the way this is a positively charged particle, okay? If it's a negatively charged particle, Q will be negative, the force will be inverse. If I, instead of, okay, suppose I have a current carrying conductor that carries a current I through it. Okay, this is the direction of the current I or J vector, right? The current through this cross section is I, and if there is a field that pierces this current carrying conductor, and this field is pointing in this direction, then what is the current? It's simply the flow of charge. If I take positive charge, the conventional current to be flowing from left to right, which is the direction of this current density, then the force is going to act on this conductor itself. Because it's the force acting on the electrons, there's a force acting on the electrons, and the electrons are within the solid matrix. So whenever the electrons experience a force, the entire solid matrix will move with it. It's not that the electrons can come out of the solid, so the solid has to move with the electrons. Okay? Because it's only the electrons that are moving, the ionic cores are fixed. So there's only a force acting on the electrons, and they will move the entire solid, the entire wire will swing. So if this is the direction of the current, now I would like to convert this charge velocity into current formula. I can do this exactly in the same way. This formula turns out to be equivalent to I dl crossed with B. Okay, this is the force acting on a small element of length dl. Sorry? The field is constant. So I take a small element dl, length dl. The force acting on this element is given by this. Okay? dl. The force acting on a small element is I dl cross B.
How did we arrive at this?
This is something you could do on your own. We've already seen this. Okay? हमने किया था जब हम यहाँ से यहाँ गए थे ना, तब हमने ये क्यों की कोई प्लेस किया था आइडियल से, बिल्कुल उसी तरह 100 डिग्री प्लेस करेंगे. Okay. Now the next lecture, I would like to discuss two things. I would like to know the practical application of this force through the cyclotron. The cyclotron is a huge machine that can accelerate particles. The second thing I would like to discuss is Ampere's law, and then we'll be done with the second premise of magnetism. Okay, so I'm going to upload a homework over the weekend. That's going to be due in a week's time, the next Monday, and the following Friday we'll have our third quiz. So these two weeks are devoted to magnetic fields exclusively. The results of the midterms will hopefully be uploaded tonight or tomorrow morning at the latest. Thank you very much.